Hi everyone, back to the real world. So here I want to talk about transformers, inductors, and these are electrical components, and this is also based on Faraday's law. Now, Faraday's law essentially gives us a way to extract energy from a magnetic field. We have a spinning coil essentially inside the magnetic field, and we use that motion to generate electric potential, and that is in a sense converting not only the kinetic energy associated with the motion of the ring, but also we can talk about changing the magnetic field itself, right? And so that changing magnetic field will also induce electric potential. So in the very first video I talked about two different ways of creating this electromotive force. We called it motional EMF, and then we had a changing magnetic flux that caused EMF. Same thing is occurring here, where we have an electrical generators associated with kind of the first type of EMF, but we can also talk about just changing the magnetic field underneath a static wire. That will also introduce an electromotive force. And that's actually what happens basically on one side of the transformer. So the idea here is that we have a way of extracting energy from a changing magnetic field, but we also know that we can generate a magnetic field, right? We can generate a magnetic field by controlling the current that runs through a particular wire, and as a consequence, I can generate a magnetic field and I can control that magnetic field. I can cause it to change, and that changing magnetic field will then induce an electromotive force in a completely separate electric circuit. And that is what's behind a transformer. You have two coils of wire, the primary and the secondary. The primary is the source in this case, so this is the thing I'm driving with my electric potential. And so what I do is I run current through this wire. This effectively becomes an electromagnet, generates a magnetic field. That magnetic field propagates through space and interacts with this coil. Now, if I just run current, DC current through here, I get a magnetic field over here, all right, but that magnetic field does nothing, right? Faraday's law is not activated because we need a changing magnetic field. So what I do is I run a changing current through here, creating a magnetic field that changes. That changing magnetic field then induces an electromotive force in this, causes current to flow. That current will oscillate back and forth. And essentially what I'm saying is that I can use alternating current on the primary to generate alternating current on the secondary. And there's no connection at all, right? These are separated just by space. There's no electrical connection. And that's one of the powers, the good thing about a transformer is that you have electrically separated circuits, but they're connected really through the magnetic field. Ampere's law generates the magnetic field. Faraday's law captures the magnetic field on the transformer. Now, how effective is that transmission? It's really due to several things. The number of wires, the number of spins on these coils has an impact, right? The more coils I have, the more magnetic field I generate. The more coils over here, the more magnetic field I capture. So there's a connection between the number of coils of wire, and that's what this formula, this is kind of the fundamental formula for a transformer, is that the ratio of these two wires is going to give me the ratio of the voltages that are experienced on the two sides of the transformer. Also, you know, the magnetic field spills out from this coil. If I can capture and through a conduit that magnetic field, I can control that magnetic flux by using an iron core, and that's typically what's done with a transformer. The purpose of this transformer core is to capture that magnetic flux, channel it from the primary to the secondary. Although strictly speaking, this will work without the core, it will just be less efficient. So that's essentially what's behind every transformer that exists. And one other thing I should point out here is that if I just consider one side, if I just have a coil of wire, a single coil of wire will act as a transformer on itself. So if I have a coil of wire generate a magnetic field through Ampere's law, create an electromagnet, that magnetic field goes from 0 to something. And so that changing magnetic field pushes back through Faraday's law on the very coil that's creating the magnetic field. This is that pushback that I mentioned earlier when we talked about diamagnetism. The fact that a source of magnetism or a changing magnetic field will actually induce a secondary magnetic field that opposes the change. That creates a kind of inertia in the electromagnetic field. And that inertia is captured in something called inductance. So for any coil of wire, any kind of contraption here with, whether it's got an iron core or whether it's just a straight up wire, will have a certain amount of self-inductance. That's what's captured in this letter L. And that represents kind of the magnetic inertia, if you will, of the field. And as a consequence, there's a potential energy associated with pushing current through a coil of wire. Now I can push current through a wire, no problem, the inductance is effectively 0. But once I coil that wire, it becomes hard to push the current through because of this back force, this resistance. And therefore that requires a certain amount of work. Even though the magnetic field does no work in and of itself, it requires work to generate that magnetic field. And this is the amount of energy that it takes to bring an inductor up to a certain current level. And this corresponds to a similar formula for the capacitor. Capacitor is 1/2 CV squared. So in the sense, I've got two parallel components. The capacitor is associated with the electric field. This inductor is associated with the magnetic field.